Okay, so first of all, thank you, Nicola and Heng Yi, for the invitation to the seminar. As Nicola said, my name is Giacomo, and today I'm going to talk about charged-current muon neutrino and neutral pion selection in MicroBooNE using Warsaw on behalf of the MicroBooNE collaboration. My presentation is going to be, I'm going to introduce a little bit of neutrino physics, at least the small relevant part to my experiment. I'm going to describe the detector and how we extract the signal up to the particle identification and the particle flow information. And then in the end, I'm going to describe our selection strategy for new MuCC and neutral pions. Okay, so I'm starting by introducing the standard model, which I imagine a lot of you already know. The standard model describes basically the existence of 3 neutrino flavors and also 3 antineutrinos, which are chargeless leptons interacting only via the weak force. According to the standard model, neutrinos have no mass, but we already know that this is not true since neutrino oscillations have been observed, and the prediction indicates the presence of mass, although we don't know what the values are. Whether or not there is more properties that have not been predicted by the standard model, we don't know yet. For sure, there are many open questions about neutrinos, like, for example, the value of the masses for the mass eigenstate, the mass ordering, which eigenstate is more massive. Does neutrino oscillation correspond to a CP violation or not? Meaning, is the probability for the neutrino type A oscillating into type B the same as the probability for antineutrino type A oscillating into antineutrino type B? Is that the same? Are, for example, the neutrinos their own antiparticles, meaning are they Dirac or Majorana particles? And last but not least, there are, we know, for now, there are 3 flavors that have been discovered, but do we have more? Are there more to be discovered? Like, for example, a stereo neutrino? Some of these questions can be answered with neutrino oscillating experiments. So I'm gonna basically tell you a little bit about what a neutrino oscillation experiment, how a neutrino oscillation experiment is done, at least for neutrinos coming from an accelerator beam. Generally speaking, we need a near detector and a far detector, and also a neutrino beam. Neutrinos are generally produced, at least for the majority, of one kind. In this case, we have neutrino B. And what we really want to do is to count the neutrino interactions happening in our near detector and far detector. Based on the ability of our detector, we can count the interactions, the neutrino interactions from type B happening in our far detector, or if it's capable, we can also count the neutrino interactions happening in our detector of type A. And this kind of allows us to study appearance or disappearance. Just keep in mind that the near detector is not necessarily a requirement of the study. The only thing is, the moment we don't have a neutrino near detector to constrain the flux of neutrinos close to the production, we are gonna face high systematics. This is obviously something we cannot escape from. So when we say we count the number of events, we need to take into account multiple factors, like, for example, the neutrino flux, the cross-section of that specific flavor, the efficiency of our detection, and also the detector response. If we're also interested in the number of events of the other flavor, meaning the flavor that has appeared in our beam, we also need to consider the oscillation probability based on the specific energy range and distance. It's also important to consider that neutrino interactions depend on the neutrino energy. For our case in MicroBooNE, the energy range is mostly included between a few hundreds MeV to a few tenths of GeV. In this range, multiple neutrino matter interactions are possible, and we can pretty much divide them into categories. The first category is neutral current. That's what we call NC, where basically we have an incoming neutrino which interacts via the Z boson. And the neutrino also represents the outgoing lepton from the interaction. These interactions are generally pretty hard to detect, since we can't really see the neutrino traveling inside our detector. And generally speaking, it's also hard to define an interaction vertex if charged particles are not produced in the interaction. The other kind that we have is the charge current, where basically the incoming neutrino is replaced by an outgoing corresponding charge lepton via the exchange of the W boson. We distinguish this case into sub cases, like for example, the quasi-elastic, where the transfer energy is low compared to the initial neutrino energy. The resonant case, it's called resonant because the nucleon in the interaction is pushed into a resonant state, which later on decays, producing a pion. And also we have the deep inelastic scattering, which is what we say the quote unquote messier one, because we have a neutrino with enough energy to resolve the quark inside the nucleon. And this interaction, most of the time, fragments the nucleon, producing many different particles. All these interactions become more or less frequent and more or less relevant based on the neutrino energy, in fact. For MicroBooNE, you can see the plot in the middle. It's the MicroBooNE energy range is given to you by the orange band, the vertical band. While for experiment like DUNE, who also uses the same technology, we're going to have a different beam, so the energy will be slightly higher. Because modern experiments are now using complex nuclei instead of, for example, hydrogen or deuterium, which was the case in the past, we can consider nucleons completely isolated anymore, and we cannot neglect the idea of the nucleons belonging to an interconnected system. There are indeed effects that we call nuclear effects that must be taken into account. And the problem is that we don't understand them completely. The models we have are not perfect. And sometimes it's hard to compare between data collected on, for example, iron to data collected on, for example, argon, because nuclear effects vary from nuclei to nuclei. So the way we traditionally describe the interactions is not so meaningful anymore, and is not complete, because now we need to consider a neutrino nucleus interaction, and we need to do that based on topology. What I mean by that is we simply need to rely on what comes out from the nucleus, since it's impossible for us to follow the chain of interaction happening inside. This basically, like, these nuclear effects vary the particle momentum and the particle multiplicity that we would expect from a traditional interaction between a neutrino and a nucleon. And so we call basically what we see, we call it the final state interaction, FSI. And in order to study now neutrino experiment, like for neutrino experiments to study neutrino interactions, we need detectors and a technology that is able to actually measure and detect what comes out from the nucleus. And so it must differentiate based on the topology that we can see later on. For example, when we have quasi-elastic events, we expect basically the neutrino to interact with the nucleon, but not to see nucleons being ejected from the nuclei. But this is indeed what we see. Or other examples, when we have a resonant case, we expect to see a pion at some point, but those pions may be absorbed before actually leaving the nucleus. And this is something that we need to consider. So here we have examples of data recorded with the Argonaut detector at Fermilab. Argonaut was one of the first liquid argon TPC, probably the first one studying neutrinos from an accelerator. And what we see here is basically the different topologies that may show up in our cases. We have all of them are charged current events. In the top left, we have, for example, a muon coming out from the nucleus. In the top right, we have a muon and also one proton. But in the bottom left, we may see, for example, two protons. The good thing is the technology we're using to detect those events is able to detect this, what's called the final state interaction. And for that, it's a good candidate to study neutrino nucleus events. So the technology is called the liquid argon time projection chamber and is a state-of-the-art neutrino detector technology with a 3D tracking capability and calorimetry for neutrino interactions that is able to detect charged particles in the final state. The technology allows for scalable detectors, which can also be built by combining multiple identical modules. It has a full angular acceptance, so we don't lose any phase space. And it basically combines information from a 2D projection of the events plus a time information, which combined allow us to create a 3D event. So bottom left, you can see an event recorded by MicroBooNE. You can make out the details of the event. You can clearly see showers, you can clearly see tracks. You can also see a delta ray, for example. While on the left, it's kind of like a sketch describing how the liquid argon TPCs work. There is an incoming neutrino, which ideally interacts inside the TPC, and it creates charged particles that are basically traveling inside the detector as well. As they travel through the argon, they both ionize and excite the argon molecules. The ionization produced in the interaction is then starts to drift toward the anode planes because of the presence of an electric field. Those charges are collected and they induce a signal on the wires planes that we have. And using the geometry and the combination of the wires, we can actually create 2D points in the plane. The combination of the drift time allows us to create the x coordinate, which is the drift coordinate, while the light created in the process can be used, for example, for triggering the event. So as you can see, there is the liquid argon technology for neutrino detection is a very active and a rich program. Its concepts come from the 70s, but in the last 20 years has been growing quickly. You can see a picture of Argonaut top left. It's basically the detector I was describing to you before. The current detector working are MicroBooNE and also Protodion. Icarus has also joined the effort at Fermilab now. It was in Italy before and now has been shipped and refurbished and in place. While SBND and DUNE are the detectors that SBND will ideally start taking data soon in like the next year or next 2 years, while DUNE is more like a long time project. Let's say this. So I'm going to talk a little bit about MicroBooNE, which is the experiment. The results I'm going to show you are recorded with. And it's basically a large TPC. The size is approximately 85 tons of liquid argon. That is its active volume. And it's a near surface detector, meaning that we will need to deal a lot with cosmics. The MicroBooNE detector sits at Fermilab, 470 meters away from the booster neutrino beam target. which is on axis, while is also able to receive neutrinos from the neutrinos at the main injector beam, which is the NUMI beam, which is off axis. MicroBooNE detects light with 32 8 inches PNTs and detects charge using 3 anode wire planes with different orientation angles. The main physics goals of the detector, of the experiment, are addressing the mini-BooNE low energy excess, what we call the LEE, achieve precise neutrino-argon cross-section measurements, and provide knowledge and experience that will serve for future liquid argon type projection chambers detectors. So I talked about this mini-BooNE low energy excess. Mini-BooNE was a Cherenkov detector located at Fermilab. Its goal was to test the liquid scintillator near detector neutrino excess. The LSND detector was an accelerator-based neutrino detector, also using Cherenkov light. While trying to test this excess, mini-BooNE 2 measured an excess of neutrino events, which belong in the low energy region. You can see in the plot top right. And hence it's called the low energy excess. The largest background for the measurement was the misidentified neutral current pion events. And the main reason is that specifically a low region, but for a Cherenkov detectors, it's hard to distinguish between electrons and single photons. Hopefully, MicroBooNE was then designed to address this problem as not being a Cherenkov detector. As you can see from the aerial view on the left, the detector sits on axis in the same beam. You can see the yellow square identifies the position of mini-BooNE, while the green square, the green rectangle, identifies the position of the MicroBooNE. The position is close. It's close to the original one, but the beam is the same. The liquid argon technology has also demonstrated the capability in discriminating electromagnetic showers from electrons and from gammas, alongside the capability in discriminating track-like particles like protons and muons. So I'm going to talk a little bit about how the detector detects the signal for the particle traveling in it, and how we transform that signal to high-level information like energy and particle identification. So the data is collected by our detector and is filtered by both hardware and software. It's converted from its original raw TPC waveform into a number of ionization electrons. Each wire is individually instrumented with the pre-amplified electronics, which operates at the cryogenic temperature. This cold electronic reduces the noise and simplifies the detector cabling, which is definitely an important aspect, as it is a crucial component of the charge readout. And it compensates for the absence of the charge amplification inside the liquid argon. Not being a gas detector with avalanche effects, for example, the charge produced in the ionization is not multiplied as the charge travels. And so the charge that is created is the charge that eventually we might be able to see. The top right panel shows how the induced signal on the 3 wire planes is deconvoluted after being cleaned by the noise filtering. And in the bottom left panel, you can see the benefit of the signal processing chain, which basically takes the raw information and returns the convoluted signal. After we clean the signal, we proceed to we proceed to the tiling phase, where basically we create 2D tiles of our event. We combine charge information with the geometry of the wires to form a triangular cells. You can see the triangular cell in the panel on the left. Each cell containing charge information is marked by a blue dot. At this point, we form blobs by looking for contiguous cells. We try to basically look for all the cells and connect them together like if they were dots, and create these blobs, which you can see here with the it's basically the blue hexagon. At this point, basically we are creating 2D slices of our event, and we can combine the time information, the drift time information, to generate a 3D object inside the TPC. This is a tomographic approach that is topology agnostic, as it doesn't depend on what kind of objects and shapes we may reconstruct inside the detector. And this is done by the Wurzel tool. We move on by dividing the entire TPC object into different clusters, as you can see on the right. To do so, we use gaps, kinks in the particles, in the objects, and the directionality of the different segments that form the TPC cluster. At this point, for each event, we have a many-to-many matching. What we do is basically we take all the TPC objects, all the TPC clusters that have been created, and we try to match them to all the PMT flashes that we have seen in the recording time window. Basically, one TPC cluster can only be matched to maximum one PMT flash, while one PMT flash can be matched to multiple TPC clusters, as they may be created in coincidence. Once the match is performed, every TPC cluster has a specific time information, which is measured by the PMT. And at this point, we can compare the cluster time to the beam time window, which is 1.6 microseconds. And we can basically reject all those TPC clusters that don't belong in that time window. In this way, we try to select our neutrino candidate. This is a better example. What you can see from on the top left is basically the XY view of our detector, Z being the direction along the beam. You can see all those clusters that have been formed because of the presence of cosmics. On the top right panel, you can see another view. It's basically the XZ view, and you can see basically like the quantity of clusters that kind of pollute our neutrino interactions. When we do this many-to-many matching and then we compare to the beam time window, we are able to only keep the specific cluster that belongs in that time frame. And as you can see, we are able to clean most of the event and only keep our new mu or our neutrino candidate. And this is pretty cool because it helps us cleaning a lot since cosmics are a real problem for us. At this point, from the selected activity, we pass to particle identification and particle flow information using a 3D multi-track trajectory and the QDX fitting of the entire TPC cluster. Each blob contains basically charge information, cell by cell. And with that information, we're also able to distinguish each cluster into track-like or shower-like, and we label them basically after selecting and differentiating between track and shower. We just proceed to label them with a particle identification that we make, and then at last we just define the primary neutrino interaction, the primary neutrino vertex. Sorry. So in order to separate the track and showers, we use 3 different techniques. We use multiple column scattering, which is mostly useful to discriminate between muons and low energy electrons. As low energy electrons behave, they produce inside the TPC a track-like cluster. We basically reconstruct the momentum from the residual range, and we compare that reconstructed momentum to the reconstructed momentum using multiple column scattering, assuming the mass of a muon. For electrons, the mass obviously is much smaller than the mass of the muon, and so the prediction should be different from what we actually measure using the residual range. Besides, as I said, electrons at low energy have a wiggler trajectory, and we can use the distance between the start and the end point, and we compare that to the total length by summing up the length of the different segments making up the track as discriminator. Obviously, for muon-like particles, the ratio will be close to 1. For electrons, the ratio will be ideally far away from 1. We also proceed identifying isolated clusters that are in proximity to other tracks or other showers in order to try to collect and put together the pieces of an electromagnetic shower. And in the end, we also use, we measure the width perpendicular to the trajectory direction in order to identify also the directionality of the electromagnetic shower. In order to reconstruct the neutrino energy, we use 3 different techniques. For a good track-like objects that stop inside the detector, it is possible to relate the range of the cluster to the kinetic energy of the particle. Basically, knowing the mass information after our PID. It's also possible to associate the dq/dx, which is the charge per unit length. We can connect that to the energy loss per unit length by a recombination model in the argon, which in this case works for both stopped and exiting particles. And for electromagnetic shower, instead, we cannot use those informations as it's kind of hard to determine a dq/dx. We simply use a charge scaling, in which basically we estimate the energy of the shower by simply scaling the total charge associated with the shower by a factor, which is derived by a Monte Carlo study. So at this point, we are ready to proceed and look at the events recorded by our detector. We know how the signal is extracted and how the high-level information is created. And our goal is to have basically an inclusive selection for new MUOC events. So why is that even important? It's important because it can function as a starting point for different measurements, which are based on the topology. We can use the new MUOC selection for signal and background constraints for the low energy excess search. Besides, precise neutrino nucleus cross-sections can lead to lower systematics the moment we want to study neutrino oscillations. And it is fundamental since LRTPC has been chosen as the technology for current and future accelerator-based neutrino oscillation experiments like SBN and DUNE. We can use this study to improve the current knowledge on nuclear effects, specifically regarding argon nuclei. And it's fundamental for better understanding neutrino-argon interactions, and as a consequence, the data we measure with the LRTPCs. The new MUOC cross-section, the new MUOC selection can also be used to understand the potentiality of the wire cell tomographic technique by comparing to existing measurements of the same kind. And yeah, this is basically like most of the motivation for studying this. Obviously, new MUOC inclusive measurement is a popular measurement, as you can see from the table presented here. Multiple experiments have done this with different nuclei as targets. Not so many use argon. We have the argon detector, which we basically said before. The mean energy of the neutrino was slightly higher, 9.6 GeV. And we also have another MicroBooNE measurement that's been done previously. The point is there was a low statistic because of the MicroBooNE decided to blind its own data for the low energy excess search, and the reconstruction algorithm was also different. So it would be nice to have a second measurement to compare. Because MicroBooNE operates at the near surface level, cosmic rays contaminate our neutrino events. Approximately, we record one neutrino interaction every 600 beam spills. And by hardware triggering only, every time we record a neutrino interaction, by the time we record a neutrino cluster, we also have recorded 20,000 cosmic clusters. So you can see now has, like, the problem is actually an important one. The example presented to you on the left shows you the number of clusters which are not neutrino induced. So in order to reject this main source of background, we apply several filters. First, we remove all the events without a PMT flash in coincidence with the time window. You can see the example in the top left sketch. In this way, we still have to deal with events without neutrino interactions, but with cosmic rays in coincidence. For example, the sketch bottom left. To handle this, we divide them into two main cases. We have through-going muons, which cross the TPC from top to bottom, for example, and are removed by studying the coordinates of the clusters. You can see on the top right panel how a through-going muon basically crosses the TPC, and you can basically study the positioning and the geometry of the cluster, and you know that your cluster started at the top, it ended at the bottom, and that might be flagged as a through-going muon. The other case is a stopped muon, which is basically a cosmic ray entering the TPC, generally from the top, and then it stops inside the TPC. We can flag them, we can tag them by studying dq in dx. And for example, we know that a stopped particle shows a Bragg peak, and we can also detect the Michel electron that comes from the muon decay. With the being of these software rejections, we can combine them all, and basically we are able to move from one neutrino event every 20,000 recorded cosmics to 5.2 neutrino interactions every single cosmic that's been recorded. This is an impressive cleaning process, and it corresponds to basically removing 99.98 cosmic ray background. At this stage, though, after cleaning all these cosmics, 15% of the remaining events is still due to this like cosmic ray background contamination. And we call this our pre-selection, meaning that it's a generic neutrino selection because it doesn't depend on the nature of the neutrino. It simply tries to remove what it's not neutrino-like. At this stage, we have a nu mu-CC efficiency of approximately 80% and a nu mu-CC purity of approximately 65%. So we can improve this selection performing a boosted decision tree classification. We can basically use the generic neutrino selection as our starting point. We can define the background taggers by hand scanning those events. That's what happened. We defined some taggers based on the remaining selected events, and we try to create those taggers to identify what kind of background we had left, mostly to reject a muon background like cosmic rays and or neutrino interactions outside the TPC, but also for neutral current events. The improved selection is completely automated, and the binary classification is built using the variables defined by those taggers. The final BDT score is the cut value is chosen by trying to maximize both efficiency and purity together. And with this strategy, the nu mu-CC selection efficiency decreases from 80% to 64%, while the purity considerably increased from 64 to 93. On the right, you can see how the efficiency and purity changes as a function of the BDT score, and we decided to cut at 0.9. This is simply a diagram that tries to simplify the strategy, the BDT strategy that we use to select nu mu-CC events. A similar approach is also used to select new ECC events, although it's outside the scope of this talk. To put it in simple words, we have each tagger defines some variables. Some variables might be scalars, which are fed directly into the final BDT, while other variables might be vectors. And so they're first converted into scalar scores by 2 rounds of BDT, which try to increase the background statistics. And then they're also fed into the final BDT for the final tagging, for the final decision. So since one of the primary goals of MicroBooNE is to address the minimum low energy excess, we constrain our selection. We constrain our new ECC selection using other channels, like, for example, the new ECC selection. And so we divide all the events selected by the generic neutrino selection. And we divide them in order to have non-overlapping and complementary sample. This means that first we perform our new ECC selection, after which we proceed with our new ECC inclusive selection of the remaining events. We split this sample into what we call Charged-Current Muon and new ECC quote unquote others, meaning what we don't think it may contain a pion. Of the left events, we simply define a NC selection, and of that, we only keep the NC pion, which might be helpful for our constraint. We also divide each sample into fully contained and partially contained events, contained obviously by the TPC. So for the moment, given the majority of the BNB dataset is blinded, we can only evaluate our selection on the open dataset, which corresponds to approximately 5.3 10 to the 19 POT, POT meaning protons on target. The majority of the selection events is labeled by new MuCC in fiducial volume that corresponds to what I called earlier new MuCC others. And corresponds to basically events with a true neutrino interaction vertex inside the TPC boundaries. So here I reported the reconstructed neutrino energy spectrum in MEV for both fully contained on the left and partially contained events on the right that have been selected by our BDT. With this limited statistics, we can notice how the partially contained events the partially contained events data in Monte Carlo agree pretty well, while for the left case, this might just simply be due to a statistic limit. So this being said, once an inclusive selection is finalized, we can start branching out, and we can proceed to select events based on the specific topology. So an exclusive selection. Like, for example, new mu pion, new mu 0 pion, 0 protons, new mu 0 pion, and protons. And basically what I'm showing you here is already a sort of selection like that. We have fully contained events on the top and partially contained events on the bottom, while on the left, it's presented to you new mu CC events with no pion containing 0 protons, while on the right, it's new mu CC events with no pion, but n protons. And so this let us study events also based on the topology and the multiplicity of specific particles. At this point, we can in fact select new mu CC events containing a pion. The selection is achieved with a box cut approach. The cut is performed on pi0 dedicated reconstructed variables, which include the invariant mass, the relative angle between the gammas visible energy, and the gap between the vertex and the gamma conversion point. The chosen value for the cut has been estimated by trying to maximize the product of efficiency and purity. And what we achieve in this way is a new MuCC pion selection with efficiency of 32% and purity of 72%. So the plots presented to you are the reconstructed invariant mass for the pion. for both fully contained and partially contained. Both of these selections will be used as data-driven constraints of the charge pion, so charge current pion background for the new ACC event selection. We can also proceed with the NC sample, and we can also try to select NC pion events. The selection cut and the approach for selecting NC pion is the same to the one used for a new MUCC pion events. We use the same reconstructed variables for the pi0, and we achieve an NC pion efficiency of 30% and NC pion purity of 45%. Again, this selection will be used to constrain our new ACC selection and our LE search. So due to the limited statistics of the currently available BNB dataset, we can rely on the other beam, which is the NUMI beam, which is off axis, but fully unblinded. The available sample corresponds to 2.1 10 to the 20 POT. And here is reported the new MUCC selection for fully contained and partially contained events as a function of the reconstructed neutrino energy in MEV. And we can see how a relatively good data Monte Carlo agreement is achieved, and it consolidates our new MUCC selection strategy. So as previously stated, we're going to use our selections in what we call a 7-channel fit strategy in order to maximize the physics sensitivity for the low energy excess search. We will use the selections on the left, so fully contained and partially contained new MUCC events, and also partially contained new ACC events to constrain the signal, which is fully contained new ACC events. In this way, we will be able to constrain the neutrino flux, the cross-section, and the detector systematics. And on the right, you also see what we will be using as background constraint, which are the charge current pi naught and neutral current pi naught samples. The idea of having 7 channels that are non-overlapping, it's basically to ensure a statistical independence among them. So in our analysis, we also consider many factors in evaluating the systematic uncertainty. For the neutrino flux and also the neutrino argon cross-section model, we use the Monte Carlo that we use in the Monte Carlo generation. We estimate the systematics with a reweighting technique. Basically, what we do is we change one parameter at a time, a parameter that is in the model, by generally plus and minus 1 sigma, and we evaluate the final selection having the parameter changed. This process leads to approximately 5 to 15% systematic error for the neutrino flux, depending on the energy beam, and also approximately 20% for the neutrino argon cross-section. You can see bin by bin the relative uncertainty of the two systematics we're considering, flux and cross-section. And this is done for all 7 channels. In addition, we evaluate what we call the dirt component, which basically constitutes in the events that the neutrino interaction happening outside the cryostat that enter our TPC. Estimating this kind of event, the number of this kind of events is relatively hard, as it depends on the environment surrounding the detector and also all the different materials around it. So we use a conservative 50% error for the number of dirt events. The proton on target number is based on proton flux measurement that's been done by the Fermilab Neutrino Facility and accounts for approximately 2%. And finally, we have the detector response, which consists in multiple factors, like the variation in the TPC waveform, the variation related to the light yield and the propagation simulation of the photons inside our TPC, variation in the space charge effects, which is basically accumulated clouds of ions that in some way distort the electric field inside the detector. And also the ionization recombination model, which may affect our energy. So at this point, what's next in our plan? We have a new MuCC cross-section on argon measurement internal node for both total and differential cross-section that soon will be presented and submitted to the MicroBooNE collaboration for an internal review. We are also going to move toward unblinding the booster neutrino beam dataset with the following strategy. So we first open what we call the far sideband, which is defined by events with high reconstructed neutrino energy, or what we define as non-new ACC-like, according to our selection. We opened the section in order to evaluate the presence of potential bugs in our selection, in our analysis, and to increase the statistics available. This is the currently in progress phase. Next, we will be moving on to the near sideband, and finally, we will unblind the entire dataset and perform the final measurement. We will be able to validate more our analysis using the full NUMI dataset, which corresponds to approximately 10 times the current statistics. The reason we're not using this full statistics yet is because it has not been processed yet. We will try to do it soon. While for the BNB, once unblinded, we will be able to access 30 times the current available statistics, which is 1.5 10 to the 21 POT. So to conclude, MicroBooNE demonstrated the capability of a fully automated, high purity and efficiency new MuCC selection using the wire cell reconstruction paradigm. Additional validation is provided by the study of new Mu data, which consolidates the results obtained with the BNB open dataset. The reconstructed neutral pion invariant mass, which is located where expected, approximately at 140 MeV, confirm the good energy reconstruction of our algorithm. And the results presented in this talk will provide a starting point for future neutrino argon cross-section measurements, as well as signal and background constraints for the low energy excess searches. Thanks.
Thanks a lot, Giacomo. Very nice talk, very interesting, and well, good luck for the future of this more statistic, the analysis with more statistics. So before releasing all the other questions from the audience, I have a quick question. So there is light detection inside the liquid argon, and you use it for the trigger, but you only use it for the trigger, or
you're talking about light, right?
Yes.
So on the side where the anode wires are, let me go back one sec. So we have like 3 anode planes, right? Yes. We also have PMTs there that are able to collect the light. And what we do is combining the BNB, the beam spill, we combine that for the data acquisition, and the light that's been produced once the neutrino event appears in the TPC can be used for what we call the many-to-many matching. Mm-hmm. In this way, we basically use it to remove cosmics. That is the main use of light in our selection. Not sure if you have a specific request with your question.
No, that's fine. That's clarifying. But you are not acquiring the data from the PMTs. You are only using them.
So what we do, like for example, in this event, you can see the red circles are basically the quantity of light that's been measured by that specific PMT. Okay. The green one is simply the prediction that we expect with Monte Carlo simulation. But we use that. We simply don't relate light measurements to, for example, energy of the particles inside the TPC. We use charge for that.
Okay, thanks a lot. So please go ahead with other question. Yes, Sasha, you have a question?
Yeah, sorry, I probably missed it. So you're talking about the background from cosmic rays, but do you also have a background from neutrons or gammas actually surrounding the detector?
So, so that specific background, it's relative to the new ECC selection and the low energy excess search, right? It's mostly it's a good source of background for that selection specifically. That's definitely been addressed. Simply, I'm not describing to you the way we do it because it's not necessarily relevant to the new MUCC selection.
Oh, okay, yeah, thank you.
Other questions? Yeah, Anki, go ahead.
So I have a question. Yeah, okay. I have a question on page 27.
Okay.
About the choice of the cut. I'm just wondering that why you don't choose the BTD score at about 0.5, but you choose around 0.9 instead.
That is a very good question. So you're saying why not positioning, for example, just a little bit to the left?
Yes, exactly.
That will increase a little bit of the efficiency and will decrease. It will probably benefit more efficiency than purity, right? Because you're moving to the left. We have specific reasons based on also error, statistical error that we want to consider. I probably don't have a plot to justify my answer, but we chose 0.9 because the purity value was a let's call it a sweet spot.
Okay. So there are concerns on except for this part, yeah. There are other concerns.
What do you mean?
You mentioned about error bars, so that means that is not included in this plot, yeah?
Yes, they're not, yes.
Okay, thanks.
Yeah.
Caleb, go ahead.
Hello, I can go. So yeah, I'm not familiar with how you like quantify the data set size because you listed a value and it was like POT. What does that mean?
Yes. So what we mean by POT is basically protons on target. And it's a way of estimating the number of neutrinos that you basically send to your detector. The way it's done, it's you start using protons, you accelerate protons to a defined energy, and the number of protons you are actually accelerating corresponds to that POT. Then later on, the moment you reach the energy range you want for the protons, you make the protons collide to a target. In these collisions, pions, kaons, and other particles are created that eventually will decay and will produce the neutrinos that like further away will correspond to your neutrino beam. So it's kind of like not a measure. It's not a direct measure of neutrinos that you that you send to the detector, but it's kind of like an indirect way.
Right. Yeah. Okay. No, thank you. That makes sense. Is it? I suppose. I guess yeah. It's easier to measure the number of protons, but
exactly
you don't necessarily know.
Yes.
How many of them end up as your initial neutrinos?
Yeah. There is like a model.
Right.
That takes into consideration like collision between proton and targets, which I think might be beryllium or something like that. And then which tells you basically the number of neutrinos that you create.
Right. Okay, thanks.
So if there are no more questions, I also have a slightly unrelated question. In slide 41, you showed the systematic errors.
Yeah.
And it is interesting to see that there are peaks.
Yes, those are related to very low statistics of events in a very low energy range. Because what we do is we change a parameter and then we evaluate down the chain the number of events that we see in that bin, right? Because the statistics in those bin is pretty small from basically like a measurement to measurement, meaning a measurement with a parameter changed by 1 sigma and a measurement done with a parameter changed by -1 sigma, you may have like a higher fluctuation, like a bigger fluctuation, and that corresponds to a higher relative uncertainty.
I see. Okay. Yeah, I was confused with the middle one, FC of neutrino in charge, because you really have peaks there, but I guess it's just a statistical fluctuation.
It simply depends on the low statistics and the statistical fluctuation of the events you may find once you change one parameter and once you change the other parameter.
Okay, very nice. So thanks a lot. We give you a virtual applause. Of course,
Thank
you have to live with that. Thanks a lot. I guess there are no more questions, and we can close this session of particle physics on the plane. Have a good day, everyone.